Hello and welcome back. Today is an exciting day as I'm going to be doing a new project using KiCad. So I want to design a flexible power supply system for development that I can use on my videos going forward. So what I will be doing is designing a circuit, a PCB that can take in 5 volts from USB and give out a 12 volt power line, a 5 volt power line, and also a 3v3 power line. I think I will add in a 3v3 LDO as well for low noise applications, if just in case I decide to do audio for this channel in the future. And then finally, I want to include a TP4056 battery management circuit and a battery protection circuit as well. So hopefully you find this video useful. So this video will focus on the design of a buck boost converter using the TPS6306 part number from Texas Instrument. So I'm going to make my tea now before I start doing the schematic capture and the PCB design. Perfect. We need the buck boost converter to operate from 3.6 volts up to 6.4 volts whilst providing a 5 volt fixed output. So you can see from here that the output current that this converter can provide is up to 2 amps in buck mode and 1.3 amps in boost mode. I'm designing this circuit to use for development, so I don't need a very high current, as most of the circuits I'll be doing will be using op amps and small low power LEDs. So I'm going to be aiming a maximum of 500 milliamps. And to reduce the time I spend on this video, I will just basically use the circuit that's been given to us on the datasheet. So if I scroll down to the circuit that I'm going to replicate, it's basically going to be this one here. So obviously this tells us that it can give us a maximum output current of 800 milliamps with an output voltage of 5 volts and with a input voltage range from 2.5 volts to 12 volts. So this will do what we need it to do. For the PCB design, I'm using KiCad as the software that will do the schematic capture and the layout. If you're new to this, you can download KiCad 7 for free from the KiCad website, so you should be able to find it very easily on Google. So first, let's go into the schematic editor and populate our schematic sheet with the things that we need in place. So you can do that by going to File and Schematics and Page Setup. So I'm going to put today's date as the issue date and revision as 1. The title of this board is Development Power Supply. The company I'm going to put down as Engineering Experience. I don't need any other information for this at the moment, but I will increase the size of the schematic to A3 as I want to add more to this board later on. So today I'm focusing on the buck boost converter, and then in the next video I'll do a boost converter. The video after that will be a buck converter and potentially doing an LDO as well. And then I'll finish off on video 4 with a TP4056 circuit and doing a charging circuit as well. So battery management and battery protection circuit. So we have the schematic sheet ready now. Let's populate it with the schematic that we need for the buck boost converter. Let's check if the TPS6306 package is available on KiCad. I'm just going to type in the part number. Would we be so lucky? So we have this part number available to use. So this is what I'm going to put down first. For this design, I'm going to use a USB-C connector as I have a lot of USB-C cables. Obviously, if you're following along, you can use whatever you like as your input. So USB-C, I just want power only. So if I can find that, that would be great. 6-pin power only. Okay, so I've got my part, the connector and my buck boost converter on the schematic now. What I'm going to do next is start adding the capacitors and the resistors into the circuit. As I showed you before, the circuit that I'm going to be following is this one here. You can see I've got two capacitors on the front here with the values of 10 microfarads. I'm going to make small changes to that. Then I've got three output capacitors with the value of 22 microfarads. Got a 1 microhenry inductor, two resistors for feedback. I have changed the value of these as I was not able to find a 111 kilo ohm resistor. So I've gone for a 200 kilo ohm resistor here and a 1.8 mega ohm resistor on the top. I don't need the power good, so I'm going to ignore that. I will potentially add in some LEDs and everything as indicators, so that the power is being supplied, and then we have the output power. So I'll add in some LEDs as well to indicate that it's working properly. The other components, we have the capacitor here on this input, and we have this capacitor here, which is to filter noise on the bottom feedback resistor. So if you want, so let's start off with the input capacitors first. To add components to the board, you can press this button here, or you can press the A key on your keyboard. And then to search for capacitors, you simply type in C, and then that will give you C as in unpolarized capacitor straight away. So from the schematic, obviously we had two capacitors at the beginning. Then we had a capacitor on pin 6 on the VAUX line. And then we had a capacitor on the feedback network, so that might go somewhere around here. And then we had two capacitors for the output, which may go somewhere around here. Obviously, we'll start organizing this as we go along. So my initial focus is on the GPS 63060 port, and then I will look at the USB-C connector. So we have an input voltage that will come from the USB-C, and the port enable pin is tied directly to the power supply rail. So to do that, you can just hover over the pin and then that gives you the wire symbol. Or you can also press this button here, or you can press the W key on your keyboard. So let's line everything up neatly. I'm going to press the W key, which stops the track wherever you are. But if you go over this, then it should already just be there. Another thing I'm going to do is add in some symbols here. So I want power, it's got 5 volts for me, that would be brilliant. So 5 volts, I'll just put this one here. And then W. And then finally I want to put some ground symbols in. Just the standard one is okay for what we're doing. So I'm not connecting anything to the PG pin, so what I'm going to do is put down a no ERC. So basically this symbol over here. So then when we do a rule check on this, it doesn't flag any issues. Let's set the capacitor values before I forget. So these are 10 microfarads. I have done a bill of materials for this, so you can see all the part numbers that are here. This is what I'll be using for the design. Sorry, from here. I will populate these part numbers later on as we select the components. I have some ideas of what components I want to use for the 12-volt boost. I haven't selected the 3v3 buck converter yet. And then I have some idea of what I'm going to use for the battery management and battery protection ICs as well. So this is C1, that's C2. So I'm adding a small value capacitor on the input, and this will help with high frequency filtering. So my apologies, these two capacitors I've changed to 22 microfarads as there were not many 10 microfarad capacitors available at the time that I selected the components. These are also 22 microfarads and we need 3 of them in parallel. The next thing I'm going to do is add in the feedback network. So pressing the component symbol again, you just type in R and you should get a resistor. The top resistor I've put down as 1.8 megohms. And the bottom resistor I've put down as 200 kilo ohms, which should give me the 5 volts output that I need. Output on this I'm going to label as 5V, and then I'm going to change the other one, V bus. So obviously this is our kind of controlled output, so 5 volts, and this is the output from the USB connector. The value of this capacitor is 10 picofarads, and for PS sync I need to connect those to the ground according to the reference design that I'm using. And then the inductor, which is in a slightly weird place for this symbol, what I'll do is just move this along and add the inductor on somewhere around here. So to do the inductor, you just want to type in L and you should get the inductor symbol. So this is basically the schematic for the buck boost converter ready. What I'm going to do now is add in the parts that I need for the USB-C connector. So for that, I need to connect the ground and the shield of the connector. So I'll connect both of those to the ground pin, and then I need two 5K1 resistors on the CC line. So this basically gives us the circuit. I have the schematic that I need. I have made sure that all the references match up with my bill of materials, as I created my bill of materials first to make sure that all the parts here are available, because I will be manufacturing this board. Let's now assign the footprints to these components. And to do that, you need to run the footprint assignment tool over here. So all of these components are equal to 0805, and the 100 nanofarad capacitor, the 10 nanofarad capacitor are both equal to the 0402 package. All 4 of the resistors have a 0402 package. So I'm going to find the resistor package here, and that's 0402. The USB-C connect, they will have something here that's power only, and then I will make sure that it matches up with the port that I have selected. I think this one's going to be close, but I'll make sure that this part works and is similar to the part that I've already selected for this. Now the inductor can be tricky. Part that I have selected is a coil craft. However, I can't find anything similar. So what I'll do is just use something that's close and then change it later on. I'm going to go with this part for now, and then we'll see if it's suitable. If it's not, I'll create a new part and I'll show you how to do that as well. This connection over here is temporary. One of the videos that I'll do in the future, I will change that connection to include the circuit for controlling where the power input is coming from. So I plan to design the circuit so that it can take the power from either a USB socket or 4 AA cells or a rechargeable battery. So I'll need to include some circuit or maybe a switch to control that. I will go through that in a later video. So let's design this part now. So I've selected all the components that we need. So I'm going to save that and go on to the PCB design. Now let's bring in the components from the schematic. So to do that, you need to press this button here or press the F8 key on your keyboard, and that will update the PCB design with any changes to the schematic. If you're doing this for the first time, just press the update PCB button, and that brings in all the components that you need. Then we have some capacitors on the input. Those are labeled with the VBus net label. We have a VBus 100 nanofarad capacitor as well. So let's bring that over this side. We have an inductor. We have the three output capacitors on this side. And then we have all of our resistors here. So the two 5K level resistors, obviously we will need to move that next to the USB-C connector, and these two resistors we can keep here. Now to make this a little bit easier to look at, what I'm going to do is remove the references and the appropriate text for now. So you can see it's a lot tidier. As I said before, the connection from the USB-C connector to here is temporary. I will change that with a power path controller later on in another video. To do a filled zone, use this function over here. So this, you can do that with Ctrl+Shift+Z, but I've never used that shortcut before. Let's put that in, and then remember this net label, so IC1L2, to tick this button. So IC1L, the clearance I will change in a little while, and the minimum width to see. I'll need to get this data from the manufacturer. I'm going to place down the zone for now. So now I've just copied that, and I'm going to mirror that horizontally. Hopefully that can just slot right in. And then if I press B, that will update the fill zones. I'm not going to take this closer to the USB-C connector yet, but what I will do is just define a edge layer just for completeness on this project. Now with that, I can also define the number of layers on this board. So to do that, you can go to your board setup, and from the board setup, you want to change the physical stack up to 4 copper layers and press OK. So now we have a 4-layer board. So what I'm going to do now is basically make the inside layer 1 the power plane and the inside layer 2 the ground plane. Obviously, if I realize at the end I don't need any of these, then I will just basically change back to a 2-layer board. But because I'm going for a slightly more complicated design, I think a 4-layer board will be ideal in this case. I'm just doing a fill zone with the ground plane on layer 3 and connecting up to the edge of our PCB. There should be some clearance between the edge of the board and the upper. So to do that, we can select this and just move it inside the board. To find out what kind of clearance you need to go to the manufacturing place and ask them. So generally they will have information on their website on what you can and can't do. So because I'm going to be deleting this layer anyway, so I'm just going to put it randomly, make sure that it's okay for now, as I'll be deleting it later when I add in my other circuits into this board. You can see the layer is connected to the ground nodes here. What I'm going to do now is add in, or make that invisible so I don't see it, and then add in my copper layers for the ground. What I'm going to do is put some wires in to connect it to the ground plane, and you can do that using this button here. But firstly, I need to define some wire sizes. I will update these later from the manufacturing house, but for now I will go for a diameter of 0.3 with a hole size of 0.15, and if that's not suitable for the manufacturing house, then I'll change that to whatever they can do. The next thing, I will connect a third zone to the 5 volts output. Now you can see I need a few more connections on this. One ground connection here, I need a ground connection there, and then I need to connect all of this to ground as well. Now that might be one too many wires, but that's alright. So you can see that's nicely connected to the ground plane. I'll do the same over here. Might not go as crazy. So let me bring the references back in play. Make all of these references smaller so that they fit in nicer. And I will check in with the manufacturing place that I'm using to make sure that I don't make them too small and that they are still legible. So I'm going to change all my character sizes to 30 by 30 with a thickness of 5, as that's something that the manufacturing house will be able to do. To do that, you need to basically go into this setting here, and then the reference designators, tick this button, and then we want to change this to this to 30, this value to 30, and line thickness to 5 mil. So let's apply that and press OK. So you can see all reference designators have changed. The last thing to do is check the inductor, because obviously I selected a random size at the beginning. So what I'll do is go to my bill of materials, load up the inductor part number, and then create a new part for this inductor. I will still continue using, I think, the layout from what it is, the 3D model, because I think it's roughly the same size. But the line pattern that I need for the inductor, which is XFL4020, is basically this here. I'll make sure I check how different the new land pattern is, or if there is a 4042 available in the XAL patterns that we found earlier. So going back to the inductor, so we got 4020, so hopefully it's the same part. So edit. So click on the inductor, press the edit button, press the E button, and then edit the footprint. So what I'm going to do now is just check that the pad sizes are what I need from this recommendation here. So pad size 1, you can see is 0.98 by 3.4, so that is correct. The second one should be the same, 0.98 by 3.4, and then the distance between the two pads is 2.37. You can see that is also correct. And then the size of this component, you can see from this drawing, is 4 mil. So let's do that. So you can see this is roughly the same size. So I'm going to continue using this part, so I don't have any issues here. And that basically means that our PCB design for now it's done. And what I will do is basically add in a boost converter, and to get the 12 volts output that we need, add in the power path controller, so maybe just some switches or maybe a dedicated IC to do that. Add in a location for the batteries, obviously, so there's quite a bit more to do on this, and this board will continue to grow in size as I do that. Obviously, for now, we have the buck boost converter designed and ready to go. So thank you for watching today, and tune in next week, hopefully, to see the next part of the design as I add in more components to this board. The main aim for me at the moment is to design a PCB that I can use for my development and my videos in the future. So after this board is done, I will have easy access to a 12 volt power supply, a 5 volt power supply, and a 3.3 volt power supply. Thank you for watching, and see you next time.